Take it away, Georgiana. Thank you very much. Okay, let's see. So 2008 and 2009 were a sad couple of years for lunar scientists who were comfortable with a nice and simple dry moon. All of a sudden we had water coming in that was being measured in inclusions in volcanic glasses. And this was used to argue for at least portions of the ancient lunar mantle to have water abundances comparable to that of the Earth's upper mantle. This water, I have to point out, is indigenous water, part of the accreted bulk composition of the moon when it formed. Also, there was a bunch of evidence coming in for water ice being observed in the permanently shadowed craters and at the lunar poles. This sort of water is water that has been delivered to the moon directly by comets or has been migrating to the poles. And then, of course, there was this discovery of widespread surfacial hydroxyl and water across the lunar surface. So I have a little disclaimer here that I have to say, and I'm going to actually read it out for you. Water is the colloquial term typically used to refer to the liquid state of the compound of hydrogen oxide or oxidane. However, it is commonly used to refer to the compound solid form, that is water ice, and also its gaseous form, water vapor. However, for the purposes of this presentation, it should be noted that although I might use the word water, liquid water is not stable on the moon. It can only exist in its solid form, water ice, dissociated form, hydroxyl, or a molecule thick layer of water that is weakly bonded to another structure. And although this latter form is technically water, to distinguish it from its liquid form, it will be represented here as HOH, not H2O. And this is so that it is distinct from its gaseous or vapor form, which also does not really occur on the moon, at least as we know it here on Earth. So, spectral reflectance observations by the Moon Mineralogy Mapper, Epoxy and Cassini showed that both hydroxyl and HOH vary spatially as a function of solar illumination geometry. So at low solar incidence angles, the observed strength of the HOH spectral H or HOH spectral feature is stronger than it is at higher angles. This means that OH and HOH abundances vary with the diurnal cycle and that these abundances also increase with increasing latitude. Such that at above approximately 60 degrees, there is a little reduction in the depth of the water-related spectral absorption bands, regardless of whatever the time of day is. So this surfacial water, which is really what I'm interested in here, that is created through the interaction of the surface of the moon with the solar wind. So the idea here goes that you have fractured mineral grains, and they will leave a partially unsatisfied chemical bonds. And these surfaces tend to have a net negative charge due to the coordination of ligands around their cation host. Solar wind protons adsorbed the negatively charged mineral surface, forming monolayer OH and HOH molecules. You can also get reduction of ferrous iron and mafic minerals to native iron, meaning that the creation of nanophase iron actually does mean the creation of water, or it could. So there is the entire lunar surface exhibits a background or equilibrium level of hydration. The abundance of it varies spatially and conditionally, well, conditionally including spatially. So the question I wonder about is what affects the amount of hydroxyl in water that can be retained in the soil. The mineralogy, the latitude, the texture, the maturity. So I'm going to go over some of these things and demonstrate to you how I've been trying to test how these things might vary with these different parameters. So beginning with mineralogy. In this map, which is from M-Cube data, it's showing in red the 2 micron depth, band depth, which is attributed to pyroxene. Green is the hydroxyl band depth, and in blue is our closest approximation of 3 micron band depth, which is attributed to water. You'll notice that the mafic areas appear red. I mean red, like they're not yellow, they're not orange. So this could be attributed to 2 things. Number 1, it could be that the maria appear to be lower in hydroxyl and water because the depth of the absorption band when it's taken from the continuum is smaller in lower albedo materials. And so therefore, it's really just this absorption band that's coming, the mafic absorption band that's coming through, not the water absorption band so much. It could also be that mafic minerals, olivine and pyroxene, do not really accommodate hydroxyl or hydrogen in their structure. Plagioclase does allow a little bit more of a wiggle room. So there's mineralogy. You could also have variation with solar incidence. At equatorial regions, the incident solar energy is greater than the bond energy for absorbed water. So as I was saying before, at lunar dawn, the increased thermal energy will drive off any overnight surface water that might have accumulated. And at latitudes greater than 60, and at the lunar dusk, the incident solar energy is low enough for hydroxyl and water to stick to grain surfaces. There could also be a variation with mineralogy and solar incidence. So work by Hibbets et al. And more recently by Poston et al. Showed that different lunar analog materials exhibit different abilities to retain water. So here we're seeing the thermal desorption curves of water from JSC 1A and albite. And the absorbed water chemisorbs at low exposure and remains present to approximately 400 degrees. A water ice peak appears at approximately 170 Kelvin, although chemisorbed waters will desorb at higher temperatures. Note that albite is more adsorbing than JSC1, with chemisorbed water dominating over ice desorption at larger exposures. Again, this could be attributed to the same phenomenon as I said before, where plagioclase can be slightly more accommodating. So there can be variation with texture. As I just showed you, that while well-ordered crystal lattices and fresh lunar minerals can provide surface charge, or even charges internally, that can provide ideal surfaces for proton absorption. Volcanic glasses, however, and amorphous coatings on mature soil grains will lack a net surface charge or really any structure within, which can retain absorbed protons. Or the weakly crystalline structure of the glass can allow for easier and more pervasive diffusion both in and out. And here also being shown from the Hibbets et al. Paper is thermal desorption curves of water on lunar analog glass, showing that it takes off at lower temperatures and pretty quickly and all at once. Possible variations with maturity. Space weathering is the physical and chemical alteration of the surface of an airless body through bombardment by meteorites in the solar wind. And these alterations are predominantly pitting creation of amorphous coatings of nanophase iron. Wow, I don't know what I've written here. Let me just try this, wing it. Okay, so you could have increased surface areas due to pitting of soil grains by micro impacts, which could allow for more more surfaces for hydroxyl and water to stick. Conversely, you can have neutralization of the surface charge because of these glassy rims being formed, and therefore not providing a net negative charge for a surface, so the hydroxyl wouldn't really want to stick so much. Or you could have hydroxyl and water trapped within vesicles or within the grain being diffused within. So all of these possible effects on the retention of hydroxyl and water leads basically to two hypotheses. Number one, hydroxyl is trapped in submicron-sized vesicles formed in glassy surface coatings on regolith particles, or diffused into these materials because of a lack of a nicely ordered crystal structure. If this is the case, any surface composition as it matures, the hydroxyl abundance will be seen to increase. Alternatively, H could adsorb to active surface sites of freshly fractured minerals. Therefore, as the Mare and highland surfaces mature, we should see hydroxyl abundance decreasing. In this previous one, it should also be noted, however, that for number two, we would also expect that fresh volcanic glasses, which already start off being glassy or having a low ordered structure, should exhibit low hydroxyl in water, but would increase slightly due to pitting as they mature because of having more surface sites, more surface area, excuse me. Okay. So here we're now testing, looking at maturity just on a normal mare surface, and we're looking at Mare tranquillitatis. This is an approximately 10-kilometer crater that I'm focusing in on here, and in the left panel, 715 nanometer reflectance. In the middle one, the maturity estimate, which is just the slope of the continuum. I apologize, this is all MQ data again. And then on the right, the 2.82 micron band depth, which is the percent band depth at 2.82 microns. The higher maturity material appears to have a greater relative abundance of hydroxyl. If you look in the maturity parameter image, we can see that there has been recent debris slides on some parts of the crater wall. In the hydroxyl parameter image, we see that these locations where recent slides have occurred correspond with relatively lower hydroxyl abundance. So from this particular analysis,
George,
it does appear
about 2 minutes.
Okay. It does appear that space weathering is causing the surface to appear to increase in hydroxyl and water. Looking at volcanic glasses, this is the peak ring of Schrodinger Basin, which is at about 75 south, and there's a pyroclastic vent and deposit within it. The Marian pyroclastic unit stands out really dark in this 2.82 micron band depth spectral parameter, which is shown on the right. I'm going to zoom in on the vent itself, and here it is in the 750 nanometer reflectance, and then in the 2.82 micron band depth. It looks pretty stripy because it is at 75 south, and the lighting geometry is pretty wacky here. However, if you look just to the top right of the vent itself, there is a fresh impact crater into the pyroclastic deposit. And it can be seen that the crater ejecta is even darker in this fresh impact in the 2.82 micron band depth image, indicating that the fresh ejecta material has an even lower OH abundance than the already low pyroclastic deposits do compared to the surrounding. Again, this does seem to be indicating that space weathering is causing the surface to increase in hydroxyl and water. And then, of course, my favorite, weird space weathering effect. So here we have 3 examples of lunar swirls at Raynor Gamma, which is on the near side, pretty close to the equator-ish, sort of. Gerasimovich, which is on the far side between Apollo and Oriental, and Mare Ingenii, which is within South Pole Aiken. In this 2.82 micron band depth image, the high albedo swirls appear darker or having a lower hydroxyl feature than off-swirl regions. And again, this is indicating that this, space weathering appears to be causing the surface of hydroxyl and water to increase with maturity. So in conclusion, there is a background level of hydroxyl and water across the lunar surface. The abundance of this varies based on latitude and the time of day, composition, texture, and maturity. And regional magnetic fields can influence this and are a great way to study the maturation effect and the effect that the solar wind has on the abundance of water. And why should we care? Well, maybe as a segue for tomorrow's talks, this water is, or locating resources for lunar exploration and habitation is very important, and these areas could be places to hone in on. This isn't just a lunar phenomenon. This is a solar system process that affects the composition of other planetary bodies, very likely, and it's a process that we could utilize to create resources for human exploration of the entire solar system and maybe beyond. And that's it.
All right, we're entertaining questions. I should mention Mike Zimmerman. Why don't you get your webcam started? I think you're next up. Let's see, I think the first, you have a couple questions here. I think the first, George, how large in diameter do you expect a fresh crater to be for its ejected material to release trapped HOH?
Probably, if you mean like the hydroxyl and water that would be trapped within the material, the ejected material, it probably doesn't have to be very large at all. Even a micrometeorite's ejecta, if it volatilizes, away it goes.
All right, Jennifer Heldman has a question. Can you say a few words about the physical processes causing this relation between less OH and surface immaturity?
Well, it's a question that I do have is it just that over time the processes of space weathering are just allowing for deeper penetration or more equilibrated diffusion, or are we actually, or is hydroxyl and water actually being trapped within the amorphous coatings on the soil, mature soil rims? I'm not quite sure. That's what I'm going with right now, or wondering about anyway.
Okay. And thermal emission of exposed rock is greater, and it may influence the thermal emission effect on the M-cube spectra, which can make them resemble less OH. Is that right? Is that possible?